Let's take a look at the following. We're going to do a quick review of the properties for expanding logarithmic expressions. Let's remember that whenever we have a log expression, if we have log base b of some quantity here, we always want the quantity inside the log to be positive. So always remember that if you find a solution when solving a logarithmic equation, make sure that you plug back that potential solution and make sure that you don't create the log of a negative quantity or the log of a zero quantity when you do that. So that's why they say when m is positive and n is positive, we have the log of a product is going to be the sum of the logs. So a log can explode when you have a multiplication in it. What else do we have? The log of a quotient is the difference of the logs, and the log of a power is a multiple of the log. The power p jumps in front and times the log. So you have those written for all the different bases. This is a generic base b right here. And then if you let b be the base 10, let's remember that when I say log base 10, or I just say log, the base is assumed to be 10. So if you don't see anything here, here or there, it's just because they let the base b be worth 10. Now, if you let the base b be e, then when you have log base e of something, it's the same as saying ln of that thing. So that's why we just have ln of the product. M times n is ln of m plus ln of n. And you have all the corresponding rules, quotient rule and power rule. So now let's go ahead and focus on the power rule. Let b and m be positive real numbers, with b being different from 1, so the base has to be other than 1. And let p be any real number. Then if you have log base b of m to the power p, again the power jumps in front, and it's p times over here the log base b of m. The logarithm of a number with an exponent is a product of the exponent and the logarithm of that number. So if you had those, 3 right here, what you have is the following. I see a power 9 on the 3, make it jump in front. So this becomes 9 log base 6 of just 3, and remember the 9 is timing that log. If you have ln of the cube root of x, let's remember that cube root means power 1/3 on x. Now this power jumps in front of the log, which is ln, which is base e, if you were to think about it. So you have 1/3 times ln of x. You could also write 1/3 log base e of x, but it would not look so elegant because log base e is called ln. So, this we like better. Okay, what about if you had log of x plus 4, the quantity x plus 4 squared, then the 2 would jump in front, so it's 2 times log of x plus 4. Notice we don't mention a base here or there because the base here is 10. And we know that log base 10 of something is just written as log of the thing. We don't emphasize the base 10. And we had also, there was the solutions coming up. So let me just not make the solution show up since I wrote it by hand. Okay, so I'm going to let you see how they do it in an interactive way. So if you have log base 6 of 3 to the 9th, it's 9 times log base 6 of 3. Then this is ln of a third, so it's 1/3 ln of x. Then this is 2 times the log of the quantity x plus 4. Okay, so now a couple of other things we'll see when we're solving our next set of equations. In 4.4, we may need those properties. If you have ln of b raised to the x over here, then you have the power x that jumps in front, so it will be x times ln of b. If you have ln of e to the x, why is it just x? Let's see. Ln of e to the x, let's see what it is. You can do it two ways. You could say this is log base e, that's what ln stands for, of e to the x. So now I'm asking you which power of the base e will give me the quantity inside the log, will give me e to the x. So I'm asking you which power should I put on this e right here in order to have the quantity inside the log, which is e to the x. So what is the mystery exponent we're looking for? What should I place for those dots? I should just put the letter x, so that it works out. So ln of e to the x, which power of e will give me the quantity inside ln, which is e to the x. We need the power x, to be the answer. That's one way to look at it. Another way to look at it is this way. If you have ln of e to the power x, this is log base e of e to the x. And you can, look at it this way, which power of e gives me e to the x. X is one answer, so that's the way I just did it. Let's do it another way. If you have ln of e to the x, you can think about it as an exponent jumping in front. So you have x times whatever ln of e is. Now, what is ln of e? Let's see. Ln of e is the same thing as log base e of e. So I claim that this quantity is 1, and that will give me an answer x times 1 or x. So why do I claim that log base e of e is just 1? Let's see. Log base e of e, also called ln of e, is really which power of e, this base hanging from the letter g, will give me the quantity inside the log, which is e. So which power should I put on e, the quantity hanging from the letter g, the base? Which power should I put on this bold b in order to get what's in the log, to get that e right here? Let's see. We know that if we take a quantity, raise it to the power 1, we get that quantity back. Is that right? So e to the first is e. So what power did I need to put right here for those dots in order to get a match? It had to be 1. So ln of e is log base e of e, which is 1. So that's what we have and what I wrote here. And the answer gives me here an x for the question, what is ln of e to the x? Okay. Now, in a similar fashion, if I have log of 10 to the x, what am I asking you? I'm asking you which power of 10, the base hanging from the letter g, will give me 10 to the x, the quantity inside the log. And let's think about that. I'm thinking of the power. Which power should I put on the bold 10? Which power should I put on the bold 10 in order to get the quantity inside the log, which is 10 to the x? Then we think about it, we say, oh, let's put the power x on that bold 10, so both sides will say 10 to the x. So which power of bold 10, the 10 that I write in bold so you can see it easily, will give me 10 to the x? The answer is x. Okay. And the last thing I wanted to show you about why this answer had to be x, the one I just did, let's take a look. If I wanted to think about it this way, log of 10 to the x, let's see. Because it's a power that I have on 10, the power x, this power x can jump in front, and this is x times log of 10. Now, what is log of 10? So I can time it by x and finish up. Log of 10, it's the same as log base 10. I'm emphasizing the base 10, log base 10 of 10. So I know it's an exponent. The answer is an exponent. It's the exponent I need to place on the 10, which I made bold over here. So which power should I put on the bold 10 hanging from the letter G over here in order to get the quantity inside the log, which is just a 10. 10 to what power gives me 10? 10 to the first power gives me 10. So log base 10 of 10, or also called log of 10, is worth 1. So if log of 10 is worth 1, then this quantity log of 10 being 1, what do I get as an answer? I get x times 1, and finishing up the question I get x, and that's the answer to what? That's the answer to log of 10 to the x. That is just x. Let's take a look at one more thing. If you have ln of e to the x, there's something you can remember. If you have the base emphasized, so this is log base e of e to the x. If you have the same base here and there, what happens, because log base e and e to a power are inverse functions of each other, they destroy each other. So then what happens is the following. This is destroyed by the log base e and e to a power are destroyed by each other, and the x falls down to the level of writing. So you just get x out of that. And if you look at the other one, log of 10 to the x, this is log base 10 of 10 to the x. Notice here the base is 10, so is this base over here. So because they're the same, they are matched, then what happens is that log base 10 and 10 to a power are inverse functions of each other that destroy each other, and x falls down. So that's not just for those two, the base e and the base 10. It's a general property that we do have that looks like this. It's called an inverse property of logs, and it goes like this. If you have log base b of the same b raised to the x, notice the base is b hanging from the g, and so is the base here b, on which you're applying the power x. So whenever you notice the same base here and there, what happens, those two destroy each other, and what you have is you're left with just x. Okay, so that's just a property.